Here we have Johannes Englsberger, also talking about Toro, right?
Well, yeah, also.
Very good. Go ahead.
Hi guys. Too loud? Okay. Can you hear me? Well. Hi guys, my name is Johannes Englsberger. I work at DLR, like George Messerson, the first speaker today. And my main focus is on locomotion, like gate generation, controls, and whole body control. Today my talk will be split in two parts. The first one is dynamic walking on moving ground, as you can see in the picture here. Walk on moving grounds. Wait a second, can we humans even do that? Oh yes, we can. As you can see here, I like this video very much. So why not like extend the capabilities of our robots to traverse terrain like this one? So as a quick outlook, this is what the proposed method can achieve. So this is a kind of split belt-like scenario where the right foot is in contact with the moving ground and the left with a fixed one. And here Toro traverses two moving plates, both in a, well, shown in a OpenHRP simulation, so quite realistic. Let me, right in the beginning, emphasize that the key ideas and features, there's two of them. One is consistency of foot trajectories with regard to ground motion, of force application points, call it ECMP, VRP, no one knows those. I know them, you should know them. Anyway, that's basically center of pressure trajectories with respect to previewed bases of support. So basically these should be feasible. And the DCM and center of mass trajectories, they should be consistent with the force application points and with the DCM terminal constraint. So basically making sure that in the end you come to a rest, so you don't fall over. The second key idea is continuity, which I will show helps for very precise tracking. So let me start out with a few basics on the divergent component of motion, which the whole method is based around. So the DCM is a linear combination between the center of mass position and its velocity, scaled by a time constant. And this definition was originally introduced by Jerry Brett for 2D, while I had extended it to 3D a few years back. And as you see, this is a point in 3D space. Now, reordering this definition yields the center of mass dynamics. Differentiating yields the DCM dynamics. As you can see, these are first order dynamics, so quite simple. And then here I already inserted the definition of the virtual repellent point, V, which encodes the total force acting on the center of mass simply by its offset from the center of mass. Very easy. The center of mass dynamics on the left is naturally stable, while the DCM dynamics is unstable. Therefore, for controls, I focus purely on the DCM, whereas for, well, different control approaches or also planning and so on, the center of mass trajectories may be of interest, so I provide closed form solutions for these as well. In my previous work, it proposed trajectory generation methods for static ground based on this DCM. So let's have a look at this previous work first. So basically I'm placing VRP waypoints, the orange ones here, well, within the expected support areas, so expected footprints. I do piecewise linear interpolation in between those, and an equation that looks like this. So basically you interpolate from like each of these start points to each of these end points, start, end, and so on, via a polynomial interpolation function. This function in time may be like first order, third order, fifth order, whatever desired continuity you want to reach. Typically I use first order, it's kind of sufficient. Then you solve the ODE for the DCM and use a DCM terminal constraint. Then you can compute DCM waypoints. This, we will see later, this is done in a matrix vector form, so super efficient. And also you can compute the corresponding continuous trajectories. Same for the center of mass, you just start with a center of mass initial constraint, compute center of mass waypoints, and continuous trajectories. So this is an overview of these trajectories, I will switch to MATLAB, which I very much love. So as you can see, here there are some random footsteps that are previewed. So you start with ECMP waypoints. That's very much related to center of pressure, just a bit cleaner or whatever. Then there's VRP waypoints, these virtual repellent point waypoints. Then you do this piecewise linear interpolation, do those reference trajectories here. You compute DCM waypoints and trajectories, center of mass waypoints and trajectories for the whole preview here. Like if you like 20 steps, 100 steps, whatever you like. And the corresponding trajectories are super continuous and nice. In 3D, this looks like that. So you see the blue point here, which is the center of mass, following the red point, that's the DCM, and this is being pushed by the green point, well, the green point up here, which is the virtual repellent point. This method, as you can see, is really very nice. I really love it. But it supports stationary grounds only. So the main idea here is to extend the exact same method to moving grounds. So the main idea here is to have a support point A that moves along a support like surface or support ground A with the corresponding velocity, and a support point B that moves along a support surface B. And then you do once again this interpolation in between these 2 points, which yields this red curve here. So basically, this red curve starts with the start point of support point A and interpolates over to the end point of support point B. This, once again, is a polynomial, just a little bit higher order. So finally, the virtual repellent point input can be formulated as a polynomial over time. This is just a collection of time monomials. And here we have the virtual repellent point polynomial parameter matrix that's built up from this support point A start point and velocity, support point B start point and velocity. This is now written in a very compact way. Now you insert the VRP in the DCM ODE, solve the first order system, very easy to solve, to yield the DCM trajectory over time using this polynomial parameter matrix and the DCM at the end of this single interpolation here as an input. These are single transition phases, as you can see on top. So there's one of these for each of the previous single transition phases. Same for the center of mass. You just take the solution for the DCM, insert it into the center of mass ODE, solve. This one is again very easy to solve. And that yields the center of mass continuous trajectory over time, taking this polynomial parameter matrix as an input, the end DCM location and the start center of mass location. Once again, this is for a single, like each and every single transition phase. Now these, like all of these single transition phases are stacked together to yield a single shot solution in matrix form. So basically what in the end you do is you specify those VRP waypoints, the corresponding velocities, and a DCM terminal constraint, which in matrix form, so this is just a stack of all of these waypoints, provides all of these waypoints in blue, and then also you have an analytical solution for these continuous trajectories here. Similar for the center of mass, you take the same boundary conditions just on top a center of mass initial constraint, which yields the center of mass waypoints in matrix form, and also the center of mass trajectories over time in continuous space. So this is how the 3D references look like. So again, switching to MATLAB. So what you see here is these red footprints, and like the red shows left footprints or foot traces. So the bold one here is where the foot starts, and then it's shifted over. The first 3 steps, like these 3 steps moving to the right, and these steps to the left. The cyan and black are the foot trajectories that are like continuously or consistently following those foot traces or footprints. And on top here, we see VRP, DCM, and center of mass trajectories, all continuous and through space consistent. So, back. So this is one of my favorite videos. I was actually too lazy to model the whole matrix of floating stepping stones. So this is walking over three-dimensional stepping stones that basically move at random velocities. The robot maneuvers itself over this moving terrain. So once again, let me recapitulate the key ideas. It's consistency of foot trajectories with regard to those moving grounds, whatever they look like, of force application points, like ECMP, VRP, trajectories with respect to the basis of support. These should be feasible. It's very much center of pressure related. And the DCM and center of mass trajectories need to be consistent with the force application point trajectories and the DCM terminal constraint. And second of all, the continuity. The advantages at a glance: the method supports a multi-step preview. They support traversing moving ground surfaces such as escalators and conveyor belts or similar moving matrices. Also, the method allows for precise tracking, trajectory tracking in the sub-millimeter range, so it's close to perfect, I would say. And it's super real-time capable because it's analytical and thus computed in microseconds. So this was part one. Let me move to part two. I was a little bit surprised, but anyway, like there came an email asking me to provide a more general perspective to my research. So I just tried to share some lessons learned or some ideas that are in my head. So my approach to research is typically a pretty naive one. So I typically like to follow my own intuition first and then do the literature research, because what I feel when I read too much too early, I tend to try to solve other people's problems instead of coming up with a potentially new solution. Then my work, I mean, pretty much, I guess that's everyone, but I still like to share it. I really like this mix of gut feeling, like an engineering intuition, and then just mathematical tools, where I'm sitting at my desk and I'm sure there exists a solution. I mean, maybe like lift higher, or maybe something like might be singularity related, and then you look into math and check the Jacobian and take the determinant. It's zero, rank drop, singularity. There you go. Then this goes back to me, once again I got an intuition. Well, how to, and so on. Maybe obvious, whatever. Like I at least for work, I like being tidy and I like being perfectionist. I have a high will to succeed, and I propose everyone should set themselves long-term goals. It should be something great, something great that you're working towards. Never give up before the scientific goal is reached to your full satisfaction, which means never give up. Then I see a high importance for debugging and visualization tools. Any state or signal in the control framework should be easy to access and check. You can only fix what you see. Once again, you can only fix what you see. Very typically, for example, I'm running into constraints within the QP and so on and so on. I don't see that. I don't check it. I don't see it. I can't fix it. If I were to see it, I was like, oh, well, look at this. That's ugly. Then we fix it. This requires a lot of logging. So basically, in my case, I use MATLAB Simulink, easy coding, debugging, whatever. With all these scopes, it's quite easy to access. Anyway, for example, in the real robot, you need a lot of logging to then offline check what actually happened. Regarding locomotion planning, I have a big love for continuous reference trajectories, as you saw. I like to call those smooth, but the mathematical sense that's not smooth, but just continuous. Yet they're kind of smooth. Yeah. Look at this. This is DCM tracking in an OpenHRP simulation, using all my filters and using the state estimation. So kind of realistic, and it's close to perfect. These are the lag torques, so I really like them because they're like there's no noise, no dirt, no nothing. And this is basically the first order interpolation, which gives you this, well, see 1 or whatever, continuity. But if you like this to vanish, go for 5th order or whatever. Then I have a strong positive opinion about long preview horizons, like not in the range of a few, like 1-2 seconds, but many steps, all steps, 100 steps if you like to, both for walking and running control. So we saw the walking trajectories. I published some work on like analytical running solutions. There, for example, I like to preview 7 steps, up to 7 steps, because that plays a role for foot placement, for example. You better know what's going to happen. Like, you better know than not know. This is, for example, it's important for foot targeting and running and stuff. I'm a very big fan of analytical solutions. Why? Because they're so easy and also real time. And I printed a T-shirt to like emphasize this: simple is difficult enough. So what I want to say with that is, like, make those building stones very like kind of simple as you can get them, in order, well, if you want to like do versatile stuff and all of those components that need to like work hand in hand, like say step adjustment and cool stuff on top. It's great if the basic stuff is simple. Regarding locomotion controls, I'm a fan of real-time optimization, local optimization of quadratic programming, kind of obviously. Actually, I started very long using inverse dynamics, but meanwhile, my colleagues from DLR, who always preach use passivity controlled approaches and so on and so on, meanwhile, I'm like moving to the other side of the river. So inverse dynamics, well, has a lower contact stability as compared to passivity-based ones. Why that? In my opinion, inverse dynamics tries to like strongly prescribe what is the dynamics that's supposed to be happening. For example, the stance foot is supposed to not accelerate. If it accelerates anyways, because maybe there's a little step or trip, or for example in the mattress, if it accelerates anyway, although you were thinking it's not accelerating, then this prescribed physics is wrong, and then stuff messes up. Whereas passivity-based approaches, basically they inscribe a behavior. So either if stuff goes right as you expected it to be, you get also perfect trajectory tracking and so on. But when, for example, the contact is unsafe, it's more of a compliant. It's a behavior. It's either good tracking or compliant, or a mix of both. So once again, like using this passivity-based whole body control framework and basically the proposed DCM trajectory generation, only not on moving ground yet, but wobbly ground. We already saw those videos, but I'd like to show them again. Yeah, like I used to work, like try to get inverse dynamics to work for I guess 3 years now. I have to admit, I'll come to that in a bit, but we just switched the IMU from 10 years old bad stuff to technical grade awesome stuff. Anyway, it took me years to not very much succeed with inverse dynamics, and now with new IMU plus passivity-based controller, there's one breakthrough hunting the other. So regarding hardware, I propose, I mean, this maybe kind of obvious, but still I want to repeat saying that try not to build a physical robot before promising simulations for that robot exist. That's related to what I like to call mechanics versus controls time constants. When I started, I thought, well, to write a controller takes me a minute, an hour, a week, or whatever. That's very fast, yes. And mechanics, oh, it's so slow, like 3 months, 3 years, whatever, to build a new hardware. And yet, in order to come up with a sophisticated controls architecture, I feel typically slower. Typically, controllers, like control guys, are very much lagging behind. Then the mechanics guys get bored, build a new hardware, no one knows how to control it, and it starts all over. So what's maybe obvious, but I still propose this once again. The mechanical design, not the construction of the actual hardware, should go hand in hand with simulations, and only once the promising simulations are achieved, go for the physical one. There's some Boston Dynamics guys here, who I'm not affiliated with, but anyway. Like Boston Dynamics guys, I have a strong favorization of good hardware. Yours is way better, but we have okay hardware as well. It's okay. And then there's some like key, well, call it insight or whatever, like key motivations that I follow, or buzzwords that I want to share. Don't estimate what can be measured. So if there's any way of measuring stuff, don't try to estimate, because typically estimation is less accurate. Rather use precise, expensive sensors, we really learned it, than imprecise, cheap ones. And don't measure, identify, calibrate, or whatever what can be built and thus known precisely. For example, a camera mounting should be like milled to like micron precision. So you don't need to calibrate and stuff. Built by expensive hardware, if any possible. If you don't have funding, that's a bit bold maybe. I never asked for funding, but apply for more funding. Go for good hardware. This can save money and especially nerves. Look at this gear part here. This part of our outdoors crane, which is the first time I tried to winch Toro up, this whole thing melted away. It's just like, that's mainly nerves in a few weeks. But anyway. And then also regarding the IMU, like this is 18,000 bucks for an IMU. Well, that's quite some money, but compared to 2 man-years of tuning, twiggling, workarounds, and so on and so on, suddenly the IMU appears, you get rid of most of the stuff. Expensive first, cheap later. Well, if you can afford it. First, solve the task using the most awesome, expensive robot, then find out how to reduce cost. And last but not least, I'm talking about my research style, so how I spread my news. I very much like international networking, like this very awesome conference here. And I really like open exchange via email or phone. Like if you guys have questions, or I actually encourage everyone to connect. Typically there's people, I read your paper, did something, didn't quite understand it, and yet, well, why didn't you write me an email or just call? And then that's my very personal style. I never forget my propaganda, like in physical paper form. So like if anyone of you is interested to, it's paper, you can touch it, you can like put your notes, and like also it never loses battery and stuff. My wife actually doesn't like the word propaganda. Like as a German, it's maybe a tiny bit tricky, but let's call it old school marketing. Like I found it actually works. So guys, if your smartphone is running out of batteries for the flight home and stuff. With that, thank you very much for your attention.
Thank you for all those questions here.
Hi, Aaron Saunders, Boston Dynamics. What do you see the belts as a surrogate for in a kind of real world?
Sorry, can you again?
What do you see the belts as? Like, are they a surrogate for something in the real world? Like, what do you think they represent for real
Moving
world locomotion?
Moving
belts.
Yeah, I mean, there's car manufacturing where some robots may want to traverse a conveyor belt. Then there's, like, if you think of a robot like in the subway, like walking up escalators, or Paternoster, I don't know if you know, but it's like kind of a always moving lift. Like that, I'm not sure where that still exists. There's or jumping on a slowly driving car or so, like walking up. I mean, there's all kinds. I think it's not so extremely academic. It's kind of like in the airport. There's those conveyor belts as well, where you want to step up. But also maybe like for understanding what humans do, like how to compensate it. I always also see it under that perspective. You can kind of learn. Yeah.
Related to that question, do you see the ability to step on a moving walkway, is that transferable to non-walkway balance tasks?
Sorry, once again, good one.
So the ability to step onto a moving walkway, if you can get a controller that does that, is that transferable to non-walkway type issues that the robot may encounter? Like slipping or...
Slipping to me is more of a QP related. thing. Like this is a planning, right? Like you don't plan for slips. Like sometimes I'm asked, yeah, do you know precisely the motion of this stuff? Yes, I do. Otherwise, I wouldn't plan for it. And like slipping, I'm not sure how that would. I would guess no. This is more of a like precise assumption of what's going to happen. And typically, you don't design stuff for slipping. You see what I mean? Also similar. I was once asked why I don't embrace the impact. First, it's non-linear, so I can solve it. Second of all, I don't preview impacts. And like I don't respect it in my planning. I try to avoid it, whatever.
Yeah. Hello, I am Darío Urbina from University of Southern California.
Yeah.
And let me explain a little bit how I see to do science. Or I see here that we show results, we show figures, and that is like the cool thing, or that is like the goal, like to get to a nice conclusion. So people are, some groups are like focused on doing software and analyzing the data, so they are nearer from getting these results. Another part of the team or different groups are more involved in designing a robot or in building a part.
Yep.
So I feel, or I have been like, I have this sense that they're like a little bit farther away from getting these results. But still, there are people that are specialized in building a robot, and there are people that are specialized in analyzing data. What would be your recommendation for those that are more into the mechanical and the design? What would be the recommendation to do and to produce these results in a faster way? Because it seems that from this perspective, they are a little bit like in a disadvantage, or they are like a little bit like farther away.
You mean the software guys or?
No, for the mechanical, or for the ones that are more in the design, like like in the hardware design. Like addressing what you have already explained, that the time you spend each time of the parts.
Maybe I'm a little bit tired today. Once again, I didn't perfectly get the point. It's about like mechanics versus like controls engineers.
Yeah, so I see it like in a timeline.
I suppose, like I suggest, first of all, the control guys to work faster, and the mechanics guys to like take it easy and like more be part of this like simulation versus design iteration process, as compared to building something that no one can use for years, because it was like just someone like came up with it. Some mechanics said, well, why not introduce like a spring in the knee? And then the controls guys said, whoa, what's that? Like it takes him 10 years, and in the 10 years the mechanic is like bored and like builds the next one. Like let's put another, like for example in DLR, that's not very much my personal preference, but where like our strategy is to build a fully compliant humanoid, like fully like actual compliance. This is just like control compliance. Springs everywhere. And as a controls guy, well, you're either like happy or wow, so many problems to solve, or like, yeah, it's gonna take me 15 years now.
Okay. So are you saying that yes, the control people or the software people or the people that analyze this data are closer to giving the results, like the ones that are going to be like results of a paper or
Sorry, they're closer to?
Are these people closer, or are they going to have more facility to give this cool or like the goal or the results of a paper or a publication? The ones in the hardware, sorry, the ones in the simulations or in the software part.
I'm sorry, I don't understand.
We can.
Okay, we'll take that one offline.
Go ahead, Aaron.
I want to ask a more technical question.
Yeah.
I take it you're planning for center of mass
Yeah.
and then implementing in the full model of the robot. I just wondered, so it seems like you have pretty small feet, and usually the feet are the way to sort of steer things.
Yep.
So how do you handle, or do you have an issue with the robot model being much more complicated than the center mass?
Not at all, because the center of mass is not a approximation, but it's just a reduced view on things. Like the center of mass of a robot, like this is not linear inverted pendulum, as you might have realized. This is just center of mass dynamics, and the center of mass of a full robot moves exactly the same as the center of mass of a point mass. So I don't see like any issue there. You just like use this because it's like linear and easy to review and so on and so on. There's actually a tiny imperfection that there's an imperfection that we want to work on. You heard me like speak about ECMP versus center of pressure and stuff. Center of pressure actually includes torque information. And this trajectory generation here doesn't take into account angular momentum effects. Therefore, in the actual whole body simulation and in the actual robot even more, you will, like, instead of this precise, like for example, foot center to foot center transfer, you will see more of a like circling around. And that obviously, it makes stuff less, like there's less of a margin of robustness in case of where circling like to the edge of the foot and now being pushed to the side. The small feet, as George already said, like some random student decided they're going to be that small, and yet we basically kind of like them because the methods have been evolved to be so like smooth and precise. Like the tracking is typically so good that even with those small feet we're able to walk. And basically now that the method is very, very good, like I had already introduced some like step adjustment stuff that we never tried in experiment. So I think now that the method is really working quite well for non-step adjusting and just center of pressure control, now adding in step adjustment will result in really good stuff.
Okay, so you can successfully plan for 7 steps ahead and you can meet that.
Okay, so we're going to cut it there because we're digging into the poster time. Go ahead, John.